Cumulative distribution functions. A cumulative distribution function is defined as the function f of x equals the probability x is less than or equal to little x. For all real numbers, x. It describes the probability of all values up to and including x. And once again, it's a function of x, where x is any real number. Let's return to an example. X is, say, the number of heads in 3 tosses of a coin. What's the probability that capital X is less than or equal to minus 0.5, for example? There are no values such that it's less than minus 0.5. That probability is 0. So for negative values of x, f of x takes on the value 0. What's the probability that x is less than or equal to 0? There is only one such value, and that is the value 0. What's the probability x equals 0? It's 1 over 2 cubed, or 1 over 8. So capital F of 0 is equal to 1/8. What's the probability of all values up to and including 1? What's f of 1? There are 2 possible values such that x is less than or equal to 1. X equals 0 and x equals 1. X equals 0 has probability 1/8. X equals 1 has probability 3/8. The sum of those two is 4/8, and so f of 1 is 4/8. And similarly, we can determine f of 2 and capital F of 3. The probability x is less than or equal to 3 is, of course, 1, because that includes all possible values of x. And similarly, the probability x is less than or equal to 4, or 5, or 3.8 is again 1, because that set includes all possible values of the random variable. What about capital F of 1.2? The probability of all the values up to and including 1.2, that includes only the values 0 and 1, which have positive probability. And so that, once again, is the same as f of 1, 4 over 8. It's probably easier to visualize a cumulative distribution function if we produce a plot of it. And for this random variable, it's a step function. This plot is that of the number of heads in 10 tosses of a coin, and so the possible values are 0, 1, 2, 3, up to 10. At each of those values, the cumulative distribution function takes a jump. We can refer to this as a step function with unequal-sized steps. At the integer value 0, it jumps by an amount equal to the probability x equals 0. That jump is imperceptible in this graph because it's so small. And at 1, once again, the jump size is the probability x equals 1. Very small, you can barely see the jump size. Whereas we have quite a high probability that x equals 5, corresponding to a large step there. Of course, the CDF is flat between integers because there is no probability on those numbers. So what properties does a cumulative distribution function have? First, it's non-decreasing, because as x increases, the probability of more and more points are being included. Second, f of x is a probability. It's the probability the random variable is less than or equal to a given number. Because it's a probability, it's always in the interval between 0 and 1. It's greater than or equal to 0, and it's less than or equal to 1. Third, what happens to f of x as we let x drift off to minus infinity? Since f of x is the probability of values to the left of x, fewer and fewer values are being included. In fact, at some point, there may be no values at all which are included in our probability calculation. And that means that the probability on those set of values is approaching 0. F of x goes to 0 as x goes to minus infinity. And there's a similar argument that applies when x goes to plus infinity. Since f of x is the probability of all values to the left of x, then we're now incorporating more and more points into our set until, as it goes to plus infinity, we've incorporated virtually all. An increasing number, that means that the probability of those points will approach 1, the maximum, the sum of the probability of every point. So as x goes to plus infinity, f of x approaches 1. As in the previous example, it might hit 1 before we get to infinity. It might hit 1 at 3 or 4 or 5, but nevertheless, at the very least, it approaches 1 as x goes to plus infinity. There is a relatively simple relationship between capital F, the CDF, and little f, the probability function of a random variable. Suppose, for example, the random variable takes only non-negative integer values. Capital F of x is the probability of those values less than or equal to x. And so if we're interested in the probability that it's equal to x, we'll take the probability of all those values up to x and subtract off those that are less than or equal to x minus 1. Little f of x, in this case, is capital F of x minus capital F of x minus 1. More generally, the probability function, f of x, is given by the size of the jump in the cumulative distribution function at a given value of x. Similarly, we can get the cumulative distribution function, capital F of x, by adding up the values of the probability function up to that point. So capital F of x is the sum over all values of z less than or equal to x of little f of z. The cumulative distribution function for the German tank problem. This is a preview of an example that you'll see later, an interesting example involving determining the number of tanks produced during the Second World War. But for the moment, let's suppose that capital N Panzer tank gearboxes are generated, and they're all labeled with serial numbers in a sequence, 1, 2, up to N. Only a few of these serial numbers, those corresponding to tanks that had been destroyed, were observed by the Allies during the war. Let's suppose we've observed little n of them. This is an example of random selection without replacement, since a destroyed tank did not appear subsequently on the battlefield. Suppose I here observe a particular value for the largest serial number of those little n. Let's suppose it's 879. What does that tell me about the total number of tanks in circulation? To answer this question, I need to know the distribution of the largest serial number observed in a sample of size little n. Let's find the probability function. Here's one solution. Let's suppose that we wish to determine the probability that the maximum serial number we observe is equal to the value little x. This means that we have to choose the tank which has serial number x, and all of our other observations have to have serial numbers less than x. There is one way of choosing the tank with serial number x, 1 choose 1, and we can fill out the rest of our sample in x minus 1 choose n minus 1 ways. There are x minus 1 smaller serial numbers. We need to select n minus 1 of them for our sample. So that's the numerator in the probability that x equals little x. The denominator, of course, the number of ways we can choose our sample with no restriction at all, namely capital N choose little n. So the probability function is the ratio of these two things, x minus 1 choose n minus 1, divided by capital N choose little n. And since we have a sample of size little n, the largest serial number we observe must be at least that. So the possible values for capital X are n, n plus 1, right up to the unknown value, presumably of capital N. Let's look at a second solution in terms of the cumulative distribution function. In order for the largest serial number to be less than or equal to little x, all little n in our sample must have serial numbers less than or equal to x. How many ways can we do this? Well, that means that of the x tanks with serial numbers less than or equal to x, we have to take a sample of n. X choose n ways. So the probability of this, the probability that capital X is less than or equal to little x, that is by definition the cumulative distribution function at x, is x choose n divided by capital N choose n. For values of x equal to n, n plus 1 up to capital N, and for other values of x, non-integral values, they're defined by their value at the next integer down, because f of x is a step function. Recall that if we wanted the probability function, little f of x, that's the size of the jump in the CDF at the point x. So we can take the difference between adjacent values of capital F of x, and it turns out, as you might expect, that we get exactly the same value for the probability function as we did under solution 1. Here's a problem you might try on your own. We'll provide a solution. Let x be the smallest number obtained when a die is rolled 3 times. Find both the cumulative distribution function, capital F of x, and the probability function, little f of x, of this random variable. You should pause now and try and solve this problem on your own. We'll give you a solution momentarily. Solution. We're asked for the probability x is less than or equal to little x. But because, in this case, we're dealing with a minimum, it's actually easier to deal with the complement, the probability that x is greater than x. Why is that? The probability that the minimum is bigger than x is the probability that the first die gives you a number bigger than x, and the second, and the third. Let's compute the probability that any one of the dice gives you a number greater than x. The probability that one die gives you a number greater than 5 is the probability that it gives you exactly 6. That's 1 out of 6 outcomes, 1/6. The probability that it's greater than 4, there are 2 outcomes, 2/6. And in general, the probability that one die gives you a number greater than x is 6 minus x over 6. So the probability that x is bigger than x is the probability all 3 dice give numbers larger than x. The first and the second and the third. The probability that the first is greater than x is 6 minus x over 6, so that's raised to the power 3. possible values of x here are 1, 2, up to 5. But we're interested in the probability that x is less than or equal to x, the complement of that event. That's f of x. And that's 1 minus the probability x is bigger than x, 1 minus 6 minus x over 6 to the power 3. And once again, that's only an appropriate formula for x equals 1, 2, up to 5. So this provides the cumulative distribution function, but we wanted values for the probability function little f of x. Recall that the probability of the value little x is the jump in the cumulative distribution function at that point, capital F of x minus capital F of x minus 1. We can write this out algebraically. This turns out to be some polynomial in x squared, but probably a little more informatively in a table below with the values of x running from 1 up to 6. You'll notice that the probability that the minimum is 1 is quite high, 91 over 6 cubed. The probability, on the other hand, that it's 6 is only 1 over 6 cubed. There's only one possibility there, and that is all 3 dice return a 6.